Hello guys, Nisim space program is here, and today we are discussing elliptical orbits. So if you haven't seen the first part, please click on the notification button. To begin with, in the last series we have seen ideally round orbit, but this is unrealistic case. In real universe all orbits are elliptical. Yes, there are some that are very close to rounds, but never a perfect, conventional round. An ellipse has two axes, minor and major one. But in our case, we need only major axis, or as astrophysicists call it, semi-major axis. The semi-major axis consists of R1 and R2. R1 is called apoapse and R2 is called periapse. The letter for semi-major axis is A, derived from average. So as I said, this letter is not for the length, but for the average. So here we have formula. A equals R1 plus R2 divided by 2. Mind that in orbital mechanics, planets, asteroids and other objects are considered point masses. However, we have to count for sizes of the objects, because they can be bigger than some galaxies and you don't want to smash into a big black hole. For every point on our elliptical orbit, we have an equation that can determine the velocity at that point. V equals square root gm or mu 2 divided by r minus 1 over a in brackets. The r here is distance from the point mass or from the center of the point mass. Gm, as you have seen in the previous episode, is very common in astrodynamics. So the astrophysicists write mu equals gm. So actually there exists a whole letter called mu. The mu for Earth is about 4 to 10 to power 14. But what happens when r equals the a, the average or the semi-major axis? This is when we get circular orbits as were shown in the previous topic and previous series. But this time the formula will look a bit different. It will look V equals mu, then open brackets 1 over A or semi-major axis, and that all in square root. This is now the exact velocity for a circular orbit. So now let's solve some examples. Zulu 1 satellite is at 300 kilometers perfectly circular orbit. It needs to go to perfect geostationary orbit. What is delta V budget it will need? So what we can do is first to determine what is geostationary orbit. It is such an orbit where the orbital velocity equals to the rate of the rotation of Earth. The velocity of the rotation of Earth is about 3000 meters per second. Delta V budget is the same as the total sum of all changes in velocities. This information is needed for calculating how much fuel do you need. So what we are going to do is to draw how our satellite will move. In the first case, it is an initial circular orbit shown in the presentation. Then it performs a change in velocity and switches on the engine to make an elliptical orbit, as shown on the slide. And the last case, when it reaches the apoapse and performs a change in velocity again to circularize the orbit. Let us start with calculating the height of initial and final orbit. Feel free to pause the video. So we can use velocity equals mu divided by a and that all in square root. So from here we can find the semi-major axis, that will be mu divided over v squared. So at the end you have to get 4.4 over 10 to power 7 meters above the center of Earth. This is our H1 or periapse. No, sorry, apoapse. Now let's find the periapse. You can use the same formula to find our periapse, and then you can find the semi-major axis. That is going to be 28,671,000 meters above the center of Earth. So from here you can find V at periapse and V at apoapse, and from there you can find how much velocity you have to put in order to make your elliptical orbit to reach the geostationary orbit. That is going to be 2830 meters per second change in velocity. Then at apoapse you can find the change in velocity you need to make your orbit circular. So if you use the math for the point of orbit, the velocity of the point of orbit, you can find 2057 meters per second. Then you can actually find the delta V circular, how much delta V you need to circularize. Then you can actually add the velocity needed for making the elliptical orbit to reach the geostationary orbit, and the velocity needed to circularize this geostationary orbit, basically to get there. And in total it should be about 3773 meters per second. This is called delta V budget. So your total delta V budget is 3773 meters per second. So this episode gave you bare basics of astrodynamics. We hope this lesson is useful, and thanks for watching. If you want to support us, please donate 10 kwacha or $1 to our project Zulu 1. The links and the information is shown below. Thank you.